What's going on, engineers? Welcome to the final, and as it turns out, the most complicated game automation I've done so far, and that's the Android game Pong using Python and OpenCV. Of course, most of you know what Python is. For those of you who don't know what OpenCV is, it's a computer vision library. It's going to allow us to actually watch the game that we're automating in real time, and it'll allow us to write software to react to certain things that happen in that game in real time. So let's just jump in and automate Pong. For those of you who are unfamiliar with the mechanics of the game Pong, it's quite simple. You simply have a ball that goes between two paddles, and then you just move the paddle to hit the ball back to one side. Eventually somebody will miss, like I'm going to miss here. Okay, I'm going to miss now. And then that's it for the game. So as far as what we need to automate, that's pretty simple, because as far as the input that we need to give to the game, it's really just this bar that can go up and down. So what we'll need to do is write something that can move that bar to any position, and then the bar would have to react to wherever the ball is. As far as writing some code to actually track the ball in real time, that's where the computer vision comes in. So I think that'll be step one. We'll put aside the part about controlling the paddle for now. We'll focus on just getting OpenCV to work to actually track the ball in real time as it goes around the screen. To start, we'll need to import CV2. That's our computer vision library, as well as a few other things that we've seen in previous videos, like NumPy and MSS and Python Pillow. Now, to watch what's happening in the game in real time, we're not actually taking a video feed necessarily. What we're doing is we're taking screenshots very rapidly, and we're just feeding those into OpenCV for processing. So to do that, we'll create a new instance of our MSS to do screenshots, and we'll start an infinite loop, which will basically read a screenshot and process it infinitely. To actually take the screenshot, we can use the grab method on SCT. And what we need to pass this is the size of the screen, and then where it should take the screenshot. So as far as what portion of the screen we want to watch, it's pretty much the entire thing here, with the exception of the buttons on the side here. And the reason we want to exclude these buttons is because you'll notice that the home button on Android looks a lot like a circle. And if we don't exclude that, we're going to get some false positives. So after using XDO tool to figure out the coordinates of everything, what this works out to be is the X position of 2560, the Y position of 1470, and then 910 pixels across and 540 pixels down. Now that we've done this, we can convert it to a NumPy array by doing np.array and provide the screen. Then we use cv2.imshow, give it a name like output, and then provide the image. What this will do is this will put the image on the screen so we can actually debug what's going on. And then we'll just add some code here so we can click the Q key to basically break out of the screen. So it should be good to test just to make sure that we actually get the image. So we'll open up the game and we'll run this code here, pong.py. And you'll see what we're actually seeing here is this is what the computer vision sees. And at the moment, it's just exactly what's over here, minus the buttons on the right-hand side. But you can see whatever we do over here is also repeated on this other screen. The thing we're going to add next is we want to draw a circle around the ball that's going across the screen. And once we have that, it should be pretty easy to determine where the paddle should be. Before we actually start detecting where the ball is, the first thing we have to do actually is get rid of this score right here. And that's because the score might be a 6, it might be a 10, and those are things that look a lot like zeros. So we actually have to basically cover that. Which is fairly simple. We can use cv2.rectangle to drop a rectangle on that. And if you actually want to see it for testing, we can change this from a black square to a green square. And then when we run it, you'll notice that that area is now covered by a green box. But we don't want it to be green, we want it to be black, so we can change this 255 back to a 0. The function that we're actually be using to detect the ball going across the screen is called huff circles. And huff circles expects a grayscale image, and right now we have a color image, so we'll have to change the color space from color to gray. So we'll create a variable called gray, and we will do cv2.cvtcolor, give it the image, and then pass it cv2.color bgr to gray. Now, you might be thinking to yourself, hold on, Pong is already black and white, why need to do this? And you're absolutely right, Pong is already black and white, but the thing is the screenshot is still taken in color, so we still have to convert it to a grayscale. Grayscale makes things a lot easier because rather than having to sort through like 16.7 million different colors, you only have to sort through 256 colors. To actually detect the circles, we create a new variable called circles. We call cv2.huffCircles. We pass it the gray version of our image and cv2.huffGradient. As far as the additional parameters supplied to the huffCircles function, I mostly just dialed those in through trial and error until I got a consistent detection of the actual ball going across the screen. The next step is going to be to actually draw a green circle around the ball as it's going across the screen. So for that, we'll start by testing if circles is not none. Next, we'll convert circles into a uint16 numpy array. And then for each point that it finds, so for pt in circles, 0, semicolon, we will draw a circle around that in green with a 5-stroke. And because the circle array is in the format of center x, center y, and then radius, we can unpack that into xyr, call cv2.circle on the image, pass it the xy as the center of the circle, and then the radius, and then the color. So I think now we're ready to run it and see if it works. So we will start our program. We can see now that there's nothing on the screen. After we click wall, you could see that there is now a red circle around the ball as it goes across the screen. So what we're doing at the moment is we're actually detecting where that circle is in real time. So this seems to be working fine. However, the one value here that's extremely important to us is actually the Y value, because that determines where the ball is up and down on the screen, which is going to determine where we need to angle our paddle. So let's rerun this again, but this time we're going to output the Y value into the console over here. And what this will do is this will show us where it is. So you can see that the higher the ball goes, the lower the number gets. The lower the ball goes, the higher the number gets. So we're just about ready to move on to step 2, which will be actually moving the paddle according to where the ball is. So the approach we're going to use for this is we're actually going to start a second thread. And that second thread is going to be responsible for looking at the current Y position of the ball and then trying to move the paddle to that Y position to match it. And the reason we have to use threading here is because it's the only way that we can keep reading screenshots really fast and move the paddle at the same time. So that means we need to actually store this Y value so that way the second thread to access it. So we'll come back up here and we'll store it in a variable called just ball Y. We'll set it to 0 by default. And then we'll come back down here and instead of printing Y, we'll do ball Y equals Y. We'll need a couple new imports to make this happen. We'll need a way to actually access the ADB client, and then we'll need to import threading so we can use threads. Then we'll need just a little more boilerplate code. It's the same code that I've used in all the other videos, and all it does is it just connects to the ADB client and allows us to send different commands to the phone. So there's 4 constant values that we'll have to establish up front to make sure that we can move the paddle in an effective manner. And the first one's going to be the center X point on the paddle, the center Y point, and then the range which the paddle can move. To save time, I've already done these ahead of time, and these are the values. The paddle is at an X position of 1700, it's at a Y position of 540, and then the minimum it can move is 160 all the way down to 920. So now it's time to construct a thread that's going to be responsible for actually moving the paddle. So we'll create a new function. I guess we'll just call it move paddle. That'll be fine. And what this will be is this will be the entry point into the new thread. We'll create a new thread called T. To do a new thread, we do threading.thread, specify a target, which will be move paddle, and then we call t.start on that. Because the move paddle function will need to modify the paddle Y variable, we need to use global paddle Y. The intent is for this thread to run pretty much until we close out of the program, so we'll introduce a new variable called running, which will default to true. And then we will run this while running. And then at the bottom here, you'll notice that once we exit, we set that running to false, and that'll cause the thread to exit. What we're interested in now is to determine where should the paddle move to. So we'll call a variable just called 2. And we'll start that as ball Y multiplied by 2. Now remember, ball Y is the variable that's constantly being updated as it determines the new ball position. The reason we have to multiply it by 2 is because our phone mirror here is actually half the size of the normal phone. So if the ball is actually at 400 pixels according to my monitor, then it's actually at 800 pixels according to the phone. If I was running this at full size, which I'm not just because it would take up the whole screen, I wouldn't be able to do anything else, then I could leave out that multiplied 2. Next we have to do is clamp the 2 value to somewhere between paddle Y min and paddle Y max. So this is as simple as doing if ball Y is less than paddle Y min, then set 2 to paddle Y min. And of course the same is true for max. So we'll just copy that, change this to max, and then instead of less than, we'll do greater than. Now if you recall from previous videos, to actually do a swipe gesture, which is what we're going to do, we want to basically swipe the paddle down a little bit. It's done in the format of input touchscreen swipe, x1, y1, x2, y2, and then the duration in milliseconds it should take to actually do the action. So of course the origin where it should move from is simple. So x1 is simply the paddle x. y1 of course is paddle y. x2 is going to be paddle x again, and that's because the x value never changes where the paddle goes. And then y2 is going to be equal to our new variable called 2. And then of course our device.shell call look like this, which is going to be input touchscreen swipe, x1, y1, x2, y2, and then a 10 millisecond duration to actually do the action. And of course, last but not least, because we actually moved the paddle, we actually have to set the paddle y value to the 2 value. And now I think it's time to test. So we'll start by doing wall mode, and then we'll turn on our code. You can see that it's moving the paddle around. So it sees the ball moving, and then it moves the paddle. Now it is kind of slow, and that's because we are up against the fact that ADP is not that fast, and that's why it's sort of glitchy. And if the ball were to go crazy, it would actually probably not do so well. Yeah, you can see that it got screwed up there. Now in a future video, I'm going to make a high performance version of this. The reason I wanted to put out a version 1 first is because the high performance version, I'm going to have to root my phone, and I just haven't done that yet. Additionally, I didn't want the version 1 to rely on somebody having a rooted phone. Anybody with Android and a Windows or Linux system can make this work no problem. Once I root my phone, that's going to allow me to do 2 things. It's going to let me stream raw video at as fast as I can possibly take it and process it. It's also going to allow me to stream the actual events directly on the device without having to go through something like ADB shell. So that means instead of getting a couple movements a second, I'm going to be able to get like 100. And that's really all there is to it. Although it didn't perform optimally, I do believe the approach is probably the best I'm going to get. And of course, if you have any questions or comments, or if you can think up of a better approach or something that I could have done better, you should definitely let me know below in the comments. And other than that, definitely be on the lookout for the high performance version of this video. And as always, I hope to see you in the next video. Take care.